Welcome back. Now it's 18.2, Occurrence and Preparation of the Representative Metals. In this section, we're going to identify natural sources of representative metals and describe electrolytic and chemical reduction processes used to prepare these elements from natural sources. So generally, we don't find the representative metals as free elements in nature. Like I said before, you can't just walk around and pick up some sodium metal from the ground. But there's lots of compounds in nature that have the metals in them as ions. For instance, lithium can be found in a lot of silicates and phosphates. Sodium and potassium are found in salt deposits. Alkaline earth metals, that's what I mean by AEM, are found in silicates, carbonates, and sulfate, with beryllium being an exception. But we can find beryllium actually in gemstones such as emerald and aquamarine. Aluminum you can find in clay and a compound called bauxite. Tin you can find in stuff called cassiterite. And lead and thallium you can find in sulfides. And then a lot of the other metals you can find as impurities in zinc or aluminum. So the metals in groups 1, 2, and then as well as aluminum don't reduce easily. So generally electrolysis is the process that we use to prepare them. So the first one is sodium, which we generally prepare using electrolysis of molten NaCl. So we melt that sodium down in what is called a Downs cell. So in the electrolysis you have your sodium chloride, we liquefy by melting it, and we use electrolysis and a lot of heat, 600 degrees Celsius, and this gives us liquid sodium metal and chlorine gas. So we also add calcium chloride to the molten sodium, and this is going to lower that melting point of the sodium chloride, which is why we're able to do this at like 600 degrees Celsius rather than the melting point of molten sodium chloride, which is actually about 801 degrees Celsius. Oops. So we can prevent the sodium and chloride ions from recombining by separating them out. So basically what happens is that chlorine gas that comes off, we're able to separate it from the system because it leaves through an outlet. And then the liquid sodium metal itself is less dense than the liquid sodium chloride, so it's able then to float to the surface and be collected. And then the chlorine gas is also stored, so because chlorine gas is also used quite a bit. So the reactions that happen at our cathode, which we'll look at in this picture, the cathode is where we have two sodium ions taking on two electrons to give us our sodium metal. And then at the anode is where we have our chlorine. We have our two chlorides combining to form chlorine gas. And so then overall then we get 2 Na plus 2 Cl minus, giving us 2 Na and Cl2. So, and then the schematic here is that of a Downs cell. We can't isolate sodium by aqueous solutions of its salts because the hydrogen ions in water are more easily reduced than sodium ions, and that would give us hydrogen gas at the cathode instead of sodium metal. So this is why we have to melt the sodium chloride, and then we get a liquid sodium metal that forms. So aluminum is prepared with electrolysis in what is called the Hall-Héroult cell. I don't know if I pronounced that right or not. And we have what is called bauxite, which is our most common source of aluminum, which we start by purifying it and then react it with hot sodium hydroxide to make sodium aluminate. And then we can remove the undissolved clay and other impurities. So this reaction and AlO, so bauxite is AlOOH, and we react that with sodium hydroxide. And then we also have our water. And so this gives us this aqueous sodium aluminate. So we have NaAlOH4. So we take out the impurities, like I was saying, like clay and other crap that's undissolved. And then we add some acid to the aluminate, sodium aluminate. And this is going to reprecipitate out aluminum hydroxide. So we take our sodium aluminate, and we give it some acid. And now we get aluminum hydroxide as a solid, so it's not soluble in water. And then sodium ions and water. So now we filter out that precipitated aluminum hydroxide. And then we heat it to make it into aluminum oxide, Al2O3. And then we can dissolve that in a mixture of cryolite. Cryolite is Na3Al(F)6. You don't have to memorize these formulas, just kind of giving you some information. And calcium fluoride. And then it goes into the cell to undergo electrolysis. And so the aluminum ions then reduce at the cathode of the Hall-Héroult cell, and then we get oxygen, carbon monoxide, and carbon dioxide that form at the cathode. Magnesium we get from seawater. It accounts for about 0.5% of seawater, but that's enough to get the magnesium we need. We do electrolysis as well to isolate it. We start by adding calcium hydroxide to the magnesium chloride from seawater to give us magnesium hydroxide. It's going to precipitate out. And then we add hydrochloric acid to dissolve it. And then we evaporate it so that way the water comes off and we're left with pure magnesium chloride. So that first step, adding the calcium hydroxide, is basically to help purify the magnesium chloride. And then we melt the magnesium chloride down, and then do electrolysis on it to get liquid magnesium and chlorine gas. What's interesting is there are facilities that don't use electrolysis at all anymore, and they use what's called the Pigeon process to chemically reduce magnesium, and we'll see that in the next slide or two. So this is the Hall-Héroult cell. So you can see where your anode and your cathode is, and it's just kind of showing you generally what's happening. Your particulates and hydrofluoric acid come out the top, and we're able then to collect our molten aluminum. It's more dense, so it goes to the bottom, and then we can collect it out the side. So chemical reduction is another way of isolating some representative metals. It is less expensive than electrolysis, and it can be done for potassium, rubidium, and cesium by reducing molten chlorides with sodium metal. So we still have to have other elements as reducing agents. So magnesium oxide is reduced using elemental silicon at high temperatures to give us pure magnesium in what is called the Pigeon process. not the bird. So we have some silicon, and we have pure silicon, solid silicon. And we're adding this to magnesium hydroxide. I'm sorry, not magnesium hydroxide, magnesium oxide. Give it some heat. And we get silicon dioxide and magnesium metal. And this accounts for over 75% of the world's production of magnesium, especially in China is where a lot of this is done. And what's interesting is this is actually not a favorable reaction for thermodynamics, but the magnesium, oops, that's not a solid, the magnesium actually comes off as a gas. So then what ends up happening is this gas, we're able to remove it, and because we're removing a product, Le Chatelier's principle comes into account and pushes the reaction to keep going in the forward direction. So we get zinc by taking zinc ores, usually zinc sulfide, zinc oxide, or zinc carbonate, and heat it in air, and that converts it to zinc oxide. And then we add some carbon in the form of coal to it to reduce the zinc oxide to zinc vapor, which we can then distill and condense. So we take in our ore, for instance, zinc sulfide, and we heat it in air, and it's the oxygen in air that's doing the work. And we get our zinc oxide, and in this case, sulfur dioxide. And then we can also, if we have zinc carbonate as our other ore, this reaction ZnCO3, give it some heat, and this becomes zinc oxide and CO2. So then, like we're saying, we take that, throw it over some carbon. So I'm just going to erase this reaction up here. You can see these reactions also in your book, where it's probably written a lot nicer. So we have now the zinc oxide and just solid carbon as coal. And this gives us gaseous zinc and carbon monoxide. And what's interesting is arsenic and cadmium we can actually distill from the zinc when we are purifying the zinc through distillation, because they have lower boiling points, so then they're going to boil off first and we can collect them. When you're at higher temperatures, you can actually get zinc distilled from lead and iron. So tin now, tin 4, the tin 4 oxide, not oxided, nice autocorrect there. It is reduced by hot coals of a campfire, and this is how it was done in ancient times. So tin 4 oxide reduction into tin metal has actually been around for a long time. Now it starts by being heated to reduce contaminants, and then we treat it with hydrochloric acid to remove the metal oxide, and then it's heated with carbon to produce tin metal. So very similar to how it was done before, but now just it starts by being purified and then heated with the carbon, which, ancient times, hot coals, that's still carbon. So now it's more, you get a more pure metal. So you've got your tin oxide, that's now pure with our carbon. And now we get give it some heat. Now we have metal tin and carbon monoxide gas. So this tin comes off generally molten. Eventually it'll solidify, and it collects on the bottom of the furnace that it's being heated in, and then it's poured into blocks to cast it.